Welcome all then to the fourth session of Statistical Learning in Practice. Today we're going to talk about model selection. So the section will be called Model Selection and Regularization, but regularization will come in the next theory session. So let me maybe, I guess I can give you a general idea as to what we wish to do in model selection. So the aim of model selection, right? I mean, generally speaking, I mean, I guess the idea is very clear. We're confronted with we have some data and we wish to sort of explain it or model it through a model, and then it's very reasonable that we may be considering a few models, if not many models, right? And so then, so for instance, you have a GLM and you have a number of covariates, and you think, well, maybe not all of them should be included, and so really this corresponds to different models, right? Depending on which covariates you use. So I call that a model as well, yeah, even if it is from the same GLM, but just different covariates included, yeah. Okay. And so then the question is, which one do we choose? And it turns out that, I mean, that in itself, we're talking about which, we're implicitly saying which of these models is best. And so, saying that something is better or worse than a different thing then requires a reference, right? And so by this, I just mean that it requires, to define a purpose, right? So depending on the purpose that we have in mind, we'll choose a model, one model or another one, with a certain criterion. Okay, so the criterion will change basically depending on the purpose. So, sort of succinctly, what I'm saying is that the aim of model selection, so aim of model selection is to have a principled way of choosing the best model from a collection for a given purpose. Yeah. So that again is important. Yeah, the purpose is important. Okay. All right. So then, what are the different purposes that we may have in mind? So one that we've already seen is the following. So for instance, we may wish to explain the data at hand as well as possible. Yeah. Okay, so really, this fits very well into what we've seen already, which is let me do maximum likelihood estimation. So what is that doing? I mean, that's exactly what the name is saying. So we take the likelihood, right? We take the likelihood sort of intuitively, meaning the probability, and then we try to maximize the probability, right? So what we do is we find the parameters that will give us, that will tell us that they were the ones that they were the most likely ones given the data that we had, yeah, that sort of generated the data. So now if you need to choose between two models that you fitted through MLE, then, so for this, let's say that, if models are nested, we can use parts 3 from theorems 1 and 2, right? So in 1 and 2, I remind you, we had this nested models, and then we could choose between them. Well, it's not really choosing between them, but we were testing, a model versus an alternative model, yeah, which was a sort of a super model. Okay, but then in this with this purpose of explaining the data as well as possible, or the data at hand as well as possible, we only know this way of of comparing nested models, but what about non-nested models, right? So there is already an open question there that we should answer. But before that, let me still argue that. So essentially for that, we'll answer it through model selection, right? So model selection will not require nestedness in the models, and so then what we wish to do is to choose, between possible sub-models, not necessarily nested. Yeah? And let's now focus on a different purpose that we could have. So we may wish to explain or to do well. To do well at unobserved data. Okay, rather than explaining the one at hand, or the observed one, yeah, the observed. Of course, the observed one is going to help us in some way, but the purpose is not really focusing on the observed one, but rather on the one that we haven't seen. So this is essentially prediction, yeah. As in, we wish to use the data in such a way that rather than we're trying to explain it, we're just trying to be, to be good at predicting what's going to happen in data that we haven't seen. Anyway, I'm just going in circles a bit. So let me then, focus a bit on, let's look at prediction. So let's dwell on it a bit, okay? So for the next few minutes. So let's go through an example. So for instance, assume we're going to analyze prediction for the following model. So assume that yi can be written as a function f of the covariates xi plus epsilon I, and this is for all I from 1 to n, so just as usual. And we're going to assume as well, just the same as in the normal in the linear model, which is that the errors are going to be 0, the variance is going to be constant. It's going to be constant. It doesn't depend on I. And the epsilons, so the errors, are uncorrelated. Yeah. Okay, so now let f hat be an estimator for f. So I remind you that an estimator is simply a measurable function of the data. So it doesn't necessarily mean that it is a good approximation to f, okay? And why am I saying this? Well, I'm saying this because we could be, for instance, looking at this in a different, sort of in a reverse direction. So we consider the linear model, we build the OLS, and then it turns out that the linear model is not the right one, but rather a more general model, that depends on some f that is not necessarily linear. But we didn't know that at first. And so the f hat is actually a linear estimator, is the OLS estimator. So there is a standing question as to, how does the OLS do when actually we don't have a linear model, but rather a more general model, right? So this is a question of robustness, basically. This is coming down to the fact that, there's a famous phrase from statistician Cox, who said, no model is correct, but some models are useful. So that's a bit, the kind of question we have here as well in mind, and is that, well, this is just a model, and let's see how it would do if it were wrong, which is with all likelihood what happens. Yeah? So it could be that it is still useful, right? Being wrong. Okay. Anyway, so if we have this f hat as being an estimator for f, then the so-called, so I'm going to define this, so the prediction or generalization or test error of f hat is given by the expectation of y star minus f at x star, and this is squared. Okay, so it's the expectation of this, where x star y star is a new and independent data point. Okay. Okay. Okay, from this model, right? Okay, so for now we haven't really, we've only said something about prediction, and for a very particular case, which is this f plus noise. And let's try to analyze this prediction error, because it will be useful for getting intuition for model selection. Yeah. Okay, so note that this guy, we can write it, so we can add and subtract certain quantities and get the following. And then, sort of expand squares and then try to compute things, and we'll get that. Excuse me, sorry, I should have written f hat here, yeah, because that's so I mean we also warn you, so here, yeah, that's what I mean, that should have a hat, yeah, and not without, because we're of course checking the error of the f hat, yeah. Okay. Okay, so then we can write, as I said, the following, and then the expectation actually is not needed in this term. So we can have here f x star minus the expectation of the f hat at x star squared plus the expectation of the expectation of f hat at x star minus f hat at x star. Excuse me that this didn't fit very well. Okay, you see what I'm doing. So I added and subtracted this guy and this guy, yeah, and then expanded squares and took the expectations. So okay, so I mean the first term, if we look at the model up there, then this should be an epsilon term, which has variance sigma squared, and so therefore this is exactly sigma squared, the first term. Yeah. The second term we're going to write as bias. Okay, so this is going to be bias of this guy and this is squared, this bias term. And then the second is a variance term. Okay, so it's the variance of this guy too. Yeah. Okay, so let's analyze each of these guys separately. So maybe let's call them I, 2, 3. Okay, so the first one is what is called the stochastic error. So stochastic, and it of course comes from the data generating mechanism. Okay, so this is clear because, you know, so in this case, in the up, sort of look upward, and, you know, it's just coming from the model that we started with, and it's not really a model. So what we're saying is that, you know, this is exactly what was giving rise to the data. That was the assumption. And so this really depends on this data generating mechanism. So I remind you that the meaning of these epsilons, you know, in some occasions, it may be that this is a measurement error, for instance, right? So we may know very well what the physical what the physical sort of relationship between the X and the Y should be, and we take measurements of that. And if we want to construct an estimator, even knowing the F, okay, so that would be a silly sort of thought process, but it's actually an important one because it makes you realize that as soon as you build an estimator, there is just no way you can go beyond, you know, a certain threshold of lack of information that comes from precisely this measurement error. A different way of sort of thinking about this is, well, if the errors represent the lack of knowledge of the world, which is, again, a particular case of that would be measurement errors, then there is just so much you can do with an estimator. There's just, you know, there is a limit as to what you can do with it. Of course, as you get more data, then it could be that you know, you have a better idea. But for this case, you know, we're only looking at how we're gonna do with this one. And anyways, so we see that there is this stochastic error, and in fact that cannot be. We have no control over this. Yeah, so no control. Okay. If we had control, then we would understand the world better. So we start by the assumption that there is just something we cannot understand. Yeah? Okay, so then the second term is what is called the bias term. And so, of course, in this case, it's squared. So it's a bias term. Okay, and so I mean, you know, it just measures how well the expectation of of our prediction explains or approximates, maybe better to approximate, the expectation of the response. And this is, of course, all for a given X star, you know, with evaluating this at a given point. Yeah? And okay, so this, in some sense, you know, if we didn't have to estimate our prediction, That's a bit of a, okay, I will go back to this. Anyway, and then the last term, what we have here is what's called the variance term. So it measures, so the variance term measuring, the expected squared error due to variability, the variability of f hat. Okay. So in some sense, what we have is that the second term is, the error that we make if we sort of remove the variability of f hat, given or induced by the data dependence, then how good is this approximation in general? And then we also have to add the variability of the estimator coming from the data. Yeah. But what is clear is that we have control, or we can control, or we control the second and the third terms via the estimator that we choose, right? So in particular, so what time is it? Half past. Okay. Let's see. So yeah. Okay. So in the linear model, yes, we need to sort of explain this a bit more detail, I think. So in the linear model, so let me just talk about the linear model. Which I remind you is just fx equals x transpose times some beta. So imagine that this is actually the data generating mechanism. Then we can choose different estimators, but we can choose the OLS, right? So the f hat x star given by x star times beta hat. Okay. So beta hat, the usual least squares estimator. And what do we get? So the bias is 0, is exactly 0, so it's unbiased. And we also know regarding the variance that the variance of this guy, sorry, I missed the transpose up here. So the variance of this guy is less or equal than the variance of this other guy for any other estimator, linear and unbiased. Okay, so this is the popular Gauss-Markov theorem, that tells us that the OLS is blue, right? So it's the best linear unbiased estimator. Okay, so therefore, if we were restricting ourselves to linear and unbiased estimators, then the OLS would have the lowest prediction ever, right? Because the prediction error would have no bias in this set of estimators, and then it would be a matter of minimizing variance, which is exactly what the OLS does. So this is what people used to do in the past. So several decades ago, they would look for unbiased estimators because they thought, well, of course, we need unbiasedness. And so now that we have unbiasedness, then let's try to look for the minimum variance. Yeah. Now, there is a key observation of modern statistics. So key observation of modern statistics is that slightly biased estimators, and of course these need to be asymptotically unbiased, but for finite samples, they can be biased, if you like. So these guys can have smaller variance, but not only that. I mean, they can have small enough variance in such a way that the prediction error is smaller. Yeah. Okay, so we can bias them a bit, and actually we get smaller variance. So you must have seen this in Principles of Statistics if you took that course last year. Okay, so in the case of the linear model, then what we have, for instance, so a way of doing this, for instance, so e.g. fit the OLS, so we're still under the model in which we think that we have a beta. So now what we're going to do is to fit OLS to a submodel, so sort of something that has less dimension than P, submodel. Okay, and then what we'll do is that, of course, this is going to be biased, right? Because we lost some ability to explain, all of the betas, so it's no longer able to explain them all. But then what will happen is that because we have less parameters, then the variance actually will decrease. Yeah? So we have less parameters to estimate, so we have the same amount of information to estimate less things, and generally speaking, that will give you less variance. You will be more certain about the value of the parameters, and so we have smaller variance. But then, of course, but not too small, right? It shouldn't be too small, because if you make the if you sort of talk or keep thinking about this, then if it is very small, then you will have introduced a lot of variance. So it may be that a lot of bias. So it may be that the variance is very small because you have one parameter to estimate, for instance, but then it will be just so far off from being able to explain a 10-dimensional model that you will have just too much bias. And so the prediction error will actually be much larger. And so what we see here is a bias variance trade-off. Okay. So I explained this in a bit more detail on the notes, as in the similar detail to what I'm talking, what I'm saying out loud. Okay. Okay. So now so what we've said is, okay, so we have a model of certain dimension, then, maybe we need to choose something a bit smaller. So what about if we have a model of a certain dimension and we start with more covariates than it includes? So also, if the true model includes P naught less than P covariates, and let's also assume for simplicity that the columns of X are orthogonal, which means that there is no correlation between the covariates, then one can compute this, and this was computed in statistical modeling, at least last year. One has that the variance of this guy, and this guy with all of the P, okay, covariates, is going to be given by the sum for all of the covariates of the entries of the X star squared over the norm of this column, the ith column of the X. And so, of course, this is a sum of non-negative terms. So, in this case too, would like to choose submodel. Okay, so in these two instances, we see that we wish to, in these sort of opposing instances, we wish to choose a submodel. So we sort of keep arguing why we need this model selection. Yeah, and then we can also yet add another case. So also, yeah, Richard, feel free to unmute. Yeah.
In that variance formula, you said if the true model only has p0 less than p covariates. I'm just confused why we're mentioning p0, but it doesn't come up in the formula.
Yeah, it doesn't, because you're just looking at the variance of the estimator that has p elements in it.
So even if it had exactly one covariate, if p0 were 1. Oh, okay.
Because the b hat here has p of them, and so think about the fact that you're going to have to estimate p different parameters, and so each of them is going to add something to the variability of the whole thing. This is what this is saying, and what exactly is each add-in is given by each term in the sum, and that doesn't really depend on the true generating data generating distribution. I mean, it does in terms of how much each term is, the value of each of the terms here in the sum, but all of them will carry some variability regardless of whether there's just one true covariate giving rise to this, or even if the model is wrong, you're still estimating like p things, so then the p things will add something to the variance.
That makes more sense. Thank you.
Okay.
Now we stop for a quick question, just to confirm the little x star is non-random in this setup?
Yes, it's non-random.
Right.
Yeah, forget about that. Yeah, forget about randomness. Yeah, a bit simpler this way. Yeah, okay, so yet a third possibility is that p is greater than n. Okay, so we're now thinking the p is so there are two things here. So we could be thinking that p is the actual size of a model, or it could be that simply like a lot of like some internet companies like Google or something, they just have like so many things that they measure for each person, and then it turns out that actually they have more of these than number of persons that they are taking data from, and they have no idea what the true model is, but still you're in this situation in which p is larger than n. So then in this case you still need to select must, well, let's say, I mean, must in the linear model, but in other models you may not. It may not be a must, but you do wish to select submodels. Ideally, so if you're in the linear model, then definitely they need to be of size at most n, right? Okay, so we've argued this through the linear model, but just a remark is that the idea, or the same idea, holds for more general models. Okay, and the idea is simple. So the more complexity of the model, of a model, the more modeling ability. I mean, this is not exactly right always, but generally you would think this. The more modeling ability, and this will mean lower bias. Yeah. But also what will happen is that you know, the difficulty of estimation, I think generally one puts the arrows on the right rather than the left, but anyway, the more difficulty in estimation, because, you know, yeah, it's just harder to estimate these things, which means that we have more variance. Yeah? And you could think the other way around. So again, what we see here is a bias variance trade-off. Okay. Okay, so let me then introduce a few ways of doing model selection, now that we've argued this. So, you know, so let's have some notation. Let this double B M be a collection of models. So this is, you know, M1 up to some M capital K collection of models, where each of them, you know, M lowercase k, is going to be, you know, we can write it as some Fk. So this is some PDF, for instance, theta k, where theta k belongs to some parameter space. So from, you know, note that I'm allowing, you know, even the parameter space to vary with each model. And we also have data. We're going to write the data as Z. So this data basically is going to be the pairs of X and Y. But, you know, more generally, we just write it like this, and we say that this is distributed according to some F naught, which is not necessarily in this collection of models. And we're going to write, you know, theta k hat for the MLE for theta k. Okay, so that should be clear. Okay, so let's introduce, given this, let's introduce so 1151, and this is different information criteria. Okay. So there are two famous, you know, information criteria, and these are the following. So let me define, so definition 4, the Akaike and Bayesian, these are two different ones, huh? Information criterion are respectively, well, criterion of a model, excuse me, of MK are given by, so AIC of MK. Yeah, so these are generally shortened as, let me write AIC and BIC, okay. So AIC of MK is by definition minus 2 log of F at the data and at the MLE, okay, plus the, you know, 2 times the dimension of the sample, sorry, of the parameter space for the kth model, and BIC sort of similarly is defined as minus 2 times the log of Fz theta k hat. But then the what is called the penalty term is a bit different. So log, we get a log rather than a 2. Okay. and the AIC and BIC of a collection of models are again respectively given by the arg min, so we wish to minimize the AIC and the BIC. Okay, so the A of each of our models, and same idea with BIC. Yeah. Okay, so it's the same thing with BIC. Okay. All right. Okay. So, I mean, these two things have actually, way of deriving these, which is quite sensible. Although we don't really have time to cover that, but I will give a couple of references in the PDF notes. But all I wish to now say, is just make a comment regarding the differences. So the penalty of BIC, as we said, is greater than the penalty of AIC. Okay, so we have this log n term rather than the 2. So what does this mean? Well, I mean, it means, of course, that AIC chooses larger models, right? By which I, of course, mean models with larger dimension. Right? Will tend to, yeah. Okay, generally, usually. Okay. Now we could also wonder, what if actually the F0, the true data generating mechanism, is contained in the collection of models that we're considering, which is of course very unlikely, but it's quite customary to, at least for mathematical statisticians, to consider this as a setting under which algorithms or decision rules are analyzed. Some people criticize this because they say, well, if we're never going to know the data generating mechanism, then what's the point of trying to understand what happens when it is contained in the models that we're proposing? Anyway, it is common to just check what happens if it is contained. So in this case, it can be shown that under some condition, BIC will select the true model. Unlike AIC. Okay, so AIC tends to be too conservative, and it takes too many parameters. Okay, so what one can conclude as a general, as a rule of thumb, is that BIC is useful for explanatory purposes, while AIC is useful for prediction purposes. Okay. I mean, I haven't really argued why it is useful for prediction purposes. That will come in a second, but you sort of expect it already, because AIC is choosing something that is a bit. It has a few more parameters than the other one, so it will introduce some bias, but yeah, okay, no, we shouldn't compare it to BIC. But generally, essentially what happens is that because it chooses a model that has more parameters, then there is more complexity to the model. So the model is able to somehow model more complicated functions, but at the same time, it will have more parameters to estimate, and that will generally mean more variance in the model, but If done carefully, then actually it can be less, and we have a prediction, better prediction error. Okay, so we'll see this in examples. Okay, so, and yeah, maybe a last point is that both can be used to choose between non-nested models. And it's important to say that we need the same data is used for both. Yeah? Same for computing the likelihoods and the MLEs. Yeah? Okay, so very quickly, let me just say 1152, which is, you know, the famous, so this is a very basic procedure that is best subset or forward selection or backward selection. Okay, so which can be in conjunction with AIC and BIC, but these just see practical 2. So we introduce them in practical 2. And then let me briefly start with cross-validation. So 1153, cross-validation. Okay, so the idea here is quite simple, and is that you know, if we could just take the data and split it into 2 sets, right? So one we would put it aside as training data, and then the other one would be testing data. So with the training data, of course, we train the model, and then once we train it, we check how well is it doing in unseen data. So that would be, you know, a way of trying to, that wouldn't be cross-validation. That would simply be just a way of, you know, trying to choose a model with a good predictive power. But then this is, of course, very costly because we're putting aside some data set that actually we could have used instead for fitting, and then the fit would have been better, right? So the idea of cross-validation is precisely to say, well, let me split the, you know, portion of the data for testing. So just the same idea, start with the same idea, train on the remaining, and then repeat, you know, the process, but holding aside different subsets. Okay. And so you know, a very popular case, or a very popular sort of type of cross-validation procedure is what is called V-fold cross-validation. Let me just write cross-val. I can shorten it as cross-val. So for instance, a GLM MK with data Z equals to XI, YI, we have the following, and I'm sorry, I'm going to use a couple more minutes. So we wish to, you know, as I said, partition one partition, and this is possibly randomly, data into V subsets of you know, approximately equal size, and I'm going to write these as XI to YI. Well, I could have written ZI simply. So ZI such that I is in some IV, and this is for V from 1 to capital V, where you know, the disjoint union of these guys equals precisely, you know, all of the possible data points. Yeah. And then second, for each V, 1 to capital V, first use, you know, your ZIs that are not in this fold that you left out as training data. To estimate your MLE for the kth model, and this is of course depending on the V. Okay. Then second, evaluate a loss function, which in this case, in the case of having a GLM, could be, for instance, the deviance. Okay, on the remaining data. And so getting the following quantity, so error of the kth model at the V fold will be the average of the evaluations at the data that we held aside. This is just this guy, mu xi transpose times the beta k at V hat. Okay, and then lastly, aggregate over all V folds to get the overall cross-validation error. So we have this cross-validation of the kth model, yeah, which is the average of these guys that we had above. Yeah. So V from 1 to capital V, and then so then choose, right? So choose. So that was the cross-validation error of a model, and therefore, if we wish to do V-fold cross-validation to choose between a collection of models, then we choose the VCV of this collection to be the argmin over K of the error that we just defined, right? Okay, so generally, just very briefly, generally, V is 5 or 10 or even N, actually. And this case is called leave one out. Cross-validation, which in many occasions is written as Luke CV, and can be shown that so asymptotically, so this is asymptotically equivalent to AIC. Okay, and so it shows that, of course, AIC is being predictive, you know, is useful at prediction, as I claimed before, because this is constructed precisely so that we have a good prediction error. You should think about that. I mean, you know, I already spoke about it a bit. And then the other way around is that, what that implies, this connection, is that the leave one out cross validation will tend to overfit. Okay. Okay. So we pause here. Happy to stay for a couple of minutes if you have any questions. Otherwise, I'll see you again on Monday for the next practical. Thank you.